Boa tarde a todas e a todos. Good afternoon. Buenas tardes. It's a good pleasure to welcome all of you for this new module of the School of Advanced Studies on Water and Society. So we are just welcoming you again to the School of Advanced Studies on Water and Society under Change. In this special module, we have the visiting of Professor Slobodan Simonovic of Western University, Canada. And also we have representatives from the São Carlos School of Engineering. So I would like to welcome, first of all, Professor Daniel Varela Magalhães. This is the president of our Center of Innovation of the School of Engineering of São Carlos. Please, Daniel, welcome to you. Thank you for coming. Also, on behalf of our director and vice director, Professor Edson Wendland and Professor Dennis Curry, they are attending their special lectures. They are teaching just now. And also, I would like to welcome Professor Slobodan Simonovic for coming and visiting Brazil. Thank you for coming. Please, in the middle, in the center here. So, please, go ahead. Also, as part of this openings ceremony, open lecture, is Professor Carlos de Oliveira Galvão from Federal University of Campina, Grande. He is joining us through video conference, and she's part of the open ceremony board. And also I would like to thank Marcelo and Junior, also our staff, for the video recording, and also Felipe Arguello de Souza. This is PhD student candidate. He has made a lot of organization stuff in person, and also just before the course, and we would like to make a very, very high and loud applause for you. Bom, muito obrigado a todos e a todas. É um prazer estar aqui novamente. Nós temos aqui pessoas de toda parte do Brasil e da América Latina também. Temos vários estudantes de fora, de várias especialidades ligadas à engenharia. So we are coming people, students from all Brazil here and South America also. PhD, Master of Science, attending graduate programs at the school, São Carlos School of Engineering. So I myself, as a chairperson of the School of Advanced Studies, I am very happy, and I'm going to share my words of this opening lecture first with Professor Daniel Varela Magalhães to make his opening words, and after Professor Slobodan Simonovic with his introductory course and open lecture. And of course, after the lecture, we have open questions and in terms of your personal views or insights. To all of you, thank you very much for coming.
Thank you, Eduardo. Well, I would like to, in the name of the director and the vice director that was supposed to come, but unfortunately they have somehow any kind of unpredicted problem. And in the name of the Engineering School of São Carlos, I would like to welcome Professor here and say to everyone that it's a privilege to have someone that's a preeminent in the field of this water business, let's say. Business is not the case, maybe. We were discussing about some particularities of this field that are managed by government mainly and not exactly by private companies. But we have always to find ways of introducing new people and new kinds of work in any kind of field, in any kind of a research area. We have in the engineering school some new challenges to deal with entrepreneurial and innovation business, and in the field of new companies, or not only people going to work in big companies. We are dealing with a challenging world. Some people call this a VUCA world, that's volatile, ambiguous, and other kinds of, and a lot of words that says about new challenging world and a changing world, okay? And then we have to deal with this. We are not so used anymore to finish our studies and go to work in a big company. Sometimes, and it happens a lot of time, that we have to do our company by ourselves. That's a new challenging world, okay? And draw a new company in this sense. So I would like to say to you that are involved in this workshop here, in this week here, that the engineering school in São Carlos is really involved on doing the support for these new initiatives that you can have. And then I can talk in the name of the Innovation Center for the engineering school in São Carlos. So if you need some support, if you want some orientation, I ask you to come and ask Professor Eduardo. He knows, I think he's the best contact. Then you can come to us. That's the main point I can talk here. And I have to say again, to enjoy the week, and then you can have the full benefits of being here and taking the chance of having the better of the area. I'm sure that you have here. Okay, thank you. Thank you for coming, Professor.
Thank you. And also to say that it's in the logos you have here, you have the Western University logo there, the Brazilian Water Agency, the Agência Nacional de Águas. Tomorrow is part of the workshop we are introducing. Also, we have the National Institute of Science and Technology of Climate Change. So we are part of this alliance. We have the Interdisciplinary Center of Climate Change, the INCLINE group. We have also the Center of Education and Research on Disasters. The CEPED is over in this right corner over there. We have, of course, CNPq, CAPES, and FAPESP foundations. They are putting the money not only to bring the professor here, but also some facilities in terms of the transfer, also in other things related to the course. I would like to thank also, of course, our department. This is the Department of Hydraulics and Sanitation Engineering. I am located there. What's more? And of course, the São Carlos School of Engineering, that's last year has the 65th birthday. So we have a history in Brazil, and of course we have to shape a legacy for the future. And you are the water leaders for the future. I am very proud to be in front of you just now, and of course sharing and trying to learn more with Slobodan in this week. It should be a very fruitful, of course, through innovation. So I am very happy. I'm going to share my happiness with you. Please enjoy the course, enjoy the lecture. Thank you very much.
Yeah, thank you very much, Mario, and thank you very much for the opportunity to be with you during this week and share some of the work and knowledge that is being generated by my research group at the University of Western Ontario. We will be talking a lot about infrastructure. We will be talking about changing conditions, and we'll be talking about resilience. That I suppose after 5 days, you will be convinced that this is the way to kind of continue working in our field. This particular lecture today is kind of introductory and opening presentation that I wanted to identify what are the driving forces that are nowadays affecting the infrastructure management. When I use the word infrastructure, I think we'll be talking more about the water-related infrastructure. And in this kind of changing conditions, try to identify what are the key challenges and what are the potential opportunities. You will be continuing along this path, and I think for you it will be quite important to understand, that we are in a really process of the major change, and that process will require finding the new ways how to continue this path of managing the existing infrastructure, dealing and designing and planning and constructing a new infrastructure, and also how to deal with the more complexity that the future conditions, these changing conditions are bringing. I like to start my presentations with conclusions. So if you don't survive until the end of the lecture, this is it. This is what I would like to say. The kind of key messages are here that the climate change will increase the water-related kind of risks and hazards. And they are overloading the current water management infrastructure, and they're changing also the design conditions for the new infrastructure that we have now to put in place and that should serve over the next number of decades. So in that period of time, a lot of things will be changing, and making today decisions with full understanding of that future change, I think it's essential. The second message is that we need to recognize the fact that these changing conditions require immediate adaptation. And I must tell you that in the country where I'm coming from, oops, what did I do? Press the wrong button. Sorry about this. The country I'm coming from, for example, during the previous government, we were not allowed to use the word adaptation. We were not allowed to use the word, climate change, where the kind of political interests are driving the process and response. I'm very happy that this has been changed with the change of the government, but we don't know what the future is going to bring to us. I think you are in a similar position. You probably are informed what's happening in the United States and other countries around the world. But this fact that we do need to adapt, I think that's the necessity. In order to understand the change and in order to kind of make attempts to adapt, we need to understand or standardize the process of performing the analysis. And science is not yet there. If anyone talks about the kind of climate change and how the climate change impacts the infrastructure, you will hear from me one way of approaching the problem, from somebody else another way. There is no standardized process yet that will tell you how to proceed with that. That brings more uncertainty into the whole process, and also puts you in a position that not only that you have to manage and answer the questions related to the infrastructure management, but you need also to answer the questions related to what is the appropriate procedure, what are the appropriate tools, techniques, methodologies that are required to bring this change into the process of design, planning, and management. And the last message I have is related to opportunities, and I will be talking about these three themes over the whole 5 days. I'll be repeating this so many times that at the end, I hope you will be convinced that that's the way to go. Opportunities are basically in reviving the way of looking at our problems as systems problems. Problems with multiple components, highly interrelated, which kind of affect each other through the set of feedback relationships. This type of view is not very common in practice. We tend to simplify, we tend to make assumptions, we tend to identify the kind of conditions and separate the components of the systems from the whole system, not taking into consideration what are the consequences of breaking some of these feedbacks. And that's where I feel systems approach will be essential opportunity to bring. Don't worry, Mario. I have one. Yeah. The second opportunity I'm going to bring is actually switch from risk to resilience. And being an engineer, resilience is receiving a lot of attention in multiple disciplines. It's a very popular term in social sciences, even in health and other areas. I'm talking about quantifying that resilience and converting resilience into a criterion that can be used to make decisions, to compare various adaptation options, alternatives, to compare our designs and response to changing conditions according to resilience as a criterion. And the final opportunity is something that is really at the beginning. The idea of actually replacing typical standards with something that I call the performance-based engineering. And through the lecture today and over the next 5 days, you will see why I think this is really something important. The changing conditions are giving us more and more trouble in fully identifying what is the exact value of a particular standard. We design a dike to meet the 100-year return period flow. What is the meaning of 100 years today? If the climate is changing, 100 years today may become 30 years tomorrow. And therefore, we need to rethink the way how the standards should be replaced. And the idea that I have here, an opportunity, I think, for young people in the future is so-called performance-based engineering. So you got the lecture. These are the kind of key messages. This is how I organized the presentation. Help me, which one is the I'm just afraid to press the wrong button, the pointer. The one in the middle? Or? Pointer should be in the back. Back, okay. The my one is different. Okay, now we know. Okay, so I organized the lecture in the following way to kind of talk a little bit about the change and provide you. I'm quite sure that you are familiar with many of these kind of introductory things. And then I'll kind of set the stage for understanding these challenges, then identify the challenges, and then kind of review the opportunities. Today, we are just going to touch on these kind of topics, spend more on this setting the stage and understanding why is this necessary. And then over the next 4 or 5 days, we will be talking a little bit more about technical issues in dealing with some of the challenges and implementing and possibly addressing some of these opportunities. So here we are. The things are changing. The population is continuing to grow around the world pretty rapidly. Major land use changes in the process. You have a huge move towards the urban areas where the large cities are becoming larger, and that land use change is affecting many of the other processes. In the same time, we are observing that the climate is changing, and changing climatic conditions together with the kind of population and land use change are interconnected in a multiple ways. The main consequence, in my opinion, of this kind of global change is the increase in the complexity of our problems, water-related problems, and also the increase in the uncertainty related to our understanding of these problems. Uncertainty in the kind of scientific description of the problems, uncertainty in the available information, uncertainty in our kind of capacity to respond. So that kind of change and outcome of the change, the complexity and uncertainty, are the kind of key factors that do require different approach to managing the water resources. In English, the saying, where the rubber hits the road is actually related to infrastructure. And when I talk infrastructure, I mean both hard and soft. So the pipes that are carrying the water are affected by the changing conditions. The transmission lines that bring the energy from the source to the demand point are affected. The roads, the airports, the bridges and so on, communications. And so we have all aspects of the physical infrastructure being subject and affected by these changing conditions. And in the meantime, because of that impact on the physical or hard infrastructure, we do experience the change in the kind of soft infrastructure, in institutional response, organization, so even the societal response. Some cultures are being affected by the changing conditions because, they cannot anymore function the way how they work. So this is quite often completely neglected, I think, from the water resources management activities, and I think it plays quite important role. And I'll share with you a little bit of my kind of philosophical approach to research in water resources field. So we have a global change resulting in complexity, increasing complexity and uncertainty. We have an impact on the physical and hard and soft infrastructure, and that's what I think we have to take into consideration. These are two pictures related to my professional life, and both are nicely kind of touching the topics of infrastructure and impact on the infrastructure of these changing conditions. The picture on the left side is the picture of the downtown of the small city in the northern part of United States, city of Grand Forks. In 1997, the area of two states in the United States, Minnesota and North Dakota, and one very large province in Canada, Manitoba, were affected by a very large flood. It was called the flood of the century on the Red River. Red River is a very specific river. It flows north. When the melt of the snow and ice occurs in the bottom parts of the watershed, the north is still under the ice, so it's very prone to flooding. 1997, I lived there. I lived through this flood, and then I was appointed by the Canadian government, Canadian and US government actually, with 5 colleagues from US and 4 colleagues from Canada, to come up with recommendations to both governments what to do in the case of floods like this. The process, how we worked over these 4 or 5 years, changed my professional life. I can teach you today very easily how to design a dike or a levee. Yeah. But I cannot tell you what are the stories that I heard in the process of working and meeting the people who suffered the consequences of that flood of 1997. This picture was a very dramatic message. It was obviously coming to Canada from the south. Yeah, I forgot to mention, this is a very large watershed, 165,000 square kilometers. And what happened is that the whole city of Grand Forks was flooded. Because of the flood, the gas lines were interrupted, and the big fire started in the downtown part of the city. Because the roads were inundated, as you can see, the people in the downtown was without help, and basically the whole downtown burned. So in the middle of water up to your neck, you see the fire completely destroying the downtown of the city. So it was such a powerful message, that kind of tells you what the changing conditions are, putting in front of us to deal with. How to deal with the problem like this, how to secure that the infrastructure, the roads will be passable so that, for example, fires can be taken care of, or how to respond and help the people that may find themselves, somewhere in the middle of something like this. And the second message, very important, it's more recent. This is the picture from 2013. The rainfall event that hit City of Toronto. City of Toronto is just 2 hours from the place where I live in the City of London. And what happened with this huge rainfall event, over 2 hours, the swollen creeks and rivers basically inundated the downtown part. And this is the picture of one of the 3 highways that go north. It's called the Black Creek. And you can see what the power of flood in this particular case can do. Obviously, the highway was built with the culvert of insufficient capacity for the event like this. And you can see the water main, the electricity lines, the gas lines, the whole infrastructure affected. The highway was closed and under the repair for months after the event. This 2 hours of rain generated approximately $1.2 billion of damage. $1.2 billion of damage for the city of Toronto. So I am using these two just to kind of tell you how these changing conditions are really changing the whole landscape of the ways and the problems and issues that we have to deal. How to protect this, how to ensure that this infrastructure will be serving what it is designed for. Should we build the culvert 3 times bigger, 5 times bigger, 10 times bigger? Who is going to answer and how to find the answer to the question? What to deal with these interconnections, fire, water, roads, people being caught in the inundated areas and so on. And that's, I think, what at least I learned as a professional, and which kind of changed my understanding of the problems, and also affected the philosophy that I'm following in trying to continue doing my research. And this is the first part of my philosophy. And that part is relatively simple, that the problems we are dealing, the water resources systems, in my opinion, should be treated as social systems. I'm an engineer, and a message like this does not set well with all the engineers. I was asked to talk about this at one very large meeting in Sweden, and I can tell you that when I was presenting this, a colleague of ours stood up, said, "You don't know what you're talking about," and left the room. So there are people who has a very strong feeling that kind of looking at the problem as a social problem is not the best way to do. The reason why I feel that this is a social problem, the water resources is a kind of social problem, is that there are some subsystems that are connected within all these different, I think, issues that we are talking about. And starting with first individuals, and then with individuals being together or working and being organized within the organizations, and then organizations playing the important role in the overall society, and all of that being kind of embedded in environment, is a kind of system that's definitely dealing with people. And that's the first part of the philosophy. The subcomponents or the subsystems, these 4 subsystems are connected, and they're very much in a permanent interaction. And the interaction is occurring through 2 types of flows of resources and flows of information. The flows of resources are determining what is the state of the system, how are the people affected, how many people are affected, what organizations are responsible for what, and how they can respond, and so on. And flow of information is kind of giving us, providing us with the feedback to understand what we are dealing with. And it's a very interesting, when you talk about the information and flow of information, every one of us may have a very different interpretation of the piece of information. I usually ask my students, what do you feel, or can you describe to me what is the flow of 10 cubic meters per second? And that all depends on basically our experience and value systems. And that's the reason why I feel that the problem or the whole area of water resources management is a social problem. So there are a lot of kind of supporting issues, but that's the first part that I am kind of trying to implement in every research project and every kind of research activity that I am involved with. And the second one is, so in a way, if you remember from the initial slide, this is helping us deal with that complexity or understanding the complexity that comes from the global change. And the second one is kind of response to the uncertainty. And in this kind of very traditional graph, I'm trying to say that managing risk, and especially moving from risk to resilience, should be considered as one of the adaptation paths to changing conditions. So because we will be making decisions under uncertainty, because the uncertainty is increasing with the globally changing conditions, the feeling is that more and more we will need to deal with this uncertainty by making decisions with incomplete knowledge. How to do that? What is the best way to do it? How to assess the risk? How to communicate the risk? How to spread the risk? There are so many associated questions with all of them, but the kind of philosophical point is that risk management in resilience assessment should be considered as the part of adaptation to change or the changing conditions. So you have my position, looking at the water as a complex social system, considering uncertainties through the risk and resilience, and that's what is kind of integrated in almost everything that I do. So, changing climate. This is a subtopic, of the presentation, and I'm going to walk you very fast through some of the basic information that I'm sure that you have seen already. What do we know? What do we know for now? We know and we measure the temperature. This is the graph that kind of shows the temperature anomaly from the period of time that was. And it's a very, very kind of clear message that we are observing. This is all up to today, that we are observing with every day the increase in the global temperature. That's known as a global warming. The black points are the observations. The red line is basically the average one. And as you can see, if you look at the last 3-4 years, every year is becoming warmer than the previous year. So that process is continuing. Some people are complaining that this is not very big change, that this is in the domain of the error. That's not correct. The black lines are actually identifying the range of error. Sorry, the blue lines are identifying the range of change, the kind of statistical value, and you can see that the change is much, much larger than what the statistics of the information. So we have a global increase in the global temperature. If you convert that and show, I have some data for Canada, and you can see this is the west coast of Canada, Vancouver Island, city of Vancouver, you probably heard. And you can see the trends in the annual minimum temperature, the mean temperature, and the bottom two graphs are corresponding precipitation. The yellow and red are very clear indication that it's becoming warmer, significantly warmer than in the past. Canada is quite north, and you realize that the more you're located to the north, you will be experiencing the higher extent of warming. The change in the temperature is through physics, changing the ability of the atmosphere to store the moisture, and by changing the ability of the atmosphere to store the moisture, the precipitation is changing too. The precipitation patterns, the precipitation intensity, and especially, I think these extreme events like, summer storms or a very large accumulation and spring runoff from the snowmelt and so on, is being basically observed in the history. You can see again the yellow and red in the presentation of the precipitation, again for the Canadian conditions, pointing out to the increase in precipitation patterns. And you have to understand that in other locations, these graphs may be showing the completely opposite impact of the changing conditions in the form of prolonged and extended droughts like you had in Brazil for years. Again, related to kind of change in the temperature that in the southern hemisphere can cause more droughts. The consequences of the kind of previous two graphs, these are some of the river basins in the same region of Canada. And you can see, I'm not going to spend too much time, but there is a kind of indication and possibility to already capture the decreasing trends. So we are facing, warmer climate. We are facing more intense or increase in the precipitation, but we are also experiencing the change in the flows that is reflecting this. What else do we know? We know that the concentration of greenhouse gases is increasing. This is a very known observation and measurements showing basically the concentration of the carbon dioxide in the atmosphere. The measurements are being done in Hawaii on the top of the mountain, very precise measurements that are capturing the difference even between the seasons and the concentration of the CO2 being affected by the leaves available to during the summertime absorb some of the CO2. The obviously very, very disturbing message is that this curve is on a very clear rising. You have to understand that this concentration is, July measurement is the last one I plotted here. It's 411 parts per million. And that the CO2 and the concentration of the CO2 in the atmosphere today is not only of importance for today, it's of importance for next 100 years, because this is how long the CO2 stays in the atmosphere. So even if we stop the emissions today completely, we will have this concentration to deal with, and the warming will continue over the longer period of time, up to 100 years. It's also interesting that we do not respond to that. This is the graph that shows the global carbon emissions from fossil fuels, published by the United Nations, and you can see a very similar picture, the concentration of the CO2 in the atmosphere and our use of fossil fuels, and basically emissions that are coming from the fossil fuels taking the same shape. Obviously, this is affecting the previous piece of information. In the same time, in the north, we have a melting of ice. Arctic is melting very seriously. The red line is showing the change on the sea ice cover or sea ice extent. The black line is showing the models. Sea ice and melting of the sea ice is a very complex physical process that models are obviously not capturing very well, because it's happening much faster than what the models are predicting. If you are brave enough to kind of plot a line through this red and see how far we are going to go, there is a possibility by 2025, 2030 that we run out of ice in the Arctic. That will be very dramatic because the albedo and the reflection of the energy that hits the Earth is majorly changing with disappearance of the white areas. This is affecting the continuation of the sea level rise and absorption of the energy that continues the warming process. So these are all these are all the kind of facts. I'm not showing you any kind of predictions of the future. These are just the measurements of what is happening and what we know up to now. Consequence of this melting, of the melting ice, is the increase in the average sea level. This is the graph that shows basically for a couple of different ways of observing, using the satellites and using the tide gauges, and you see pretty good agreement. The satellites were started to be used much later in the process, that basically sea level is rising, and it's rising much faster than we were predicting. The NASA is posting regularly the measurements, and I took the last measurement, which is indicating the increase of up to 94 millimeters with the error of measurement of plus minus 4. These are very dramatic changes, and you realize that there is approximately 80% of the world population which actually lives in coastal areas. So the consequences of the sea level rise are going to be very dramatic and affect, obviously, the population in these areas. So the conclusion of these facts that are kind of known is that observational data actually underscore the concerns about the global change. And some of the previous projections summarized by the Intergovernmental Panel of Climate Change have not exaggerated the message, but maybe even underestimated the consequences and the changing that's occurring, particularly with the sea level rise and the melt of the ice in the Arctic. And why do we worry about this? That's why we worry. We are initiating something, or we initiated something that is kind of going to go around, and the question is what is going to happen with us when this last domino kind of finally falls. So we are changing the kind of key feedback and do not realize that change being caused by our activities, use of fossil fuels in power generation, in transport, and so on, is actually part of the main feedback that's going to affect the way how we live, the way how the disasters are going to hit us, and the way how we are going to, survive in the future. The link between the climate and social adaptation is a closed feedback loop. The change in our kind of adaptation or adapting to particular condition is changing the climate, and the climate requires us to kind of adapt. So you have that kind of permanent feedback that's working, and the sad story is that this feedback is called positive feedback, and in the systems theory, positive feedbacks are basically destabilizing the systems until you introduce some measures that can introduce some negative feedback and try to control the positive feedbacks. Are the types of feedbacks that you can see in the stock exchange failure, or the economic recessions and things like that. They are kind of feed each other and basically destabilize systems. We have some facts that are already documenting these positive feedbacks. Higher temperature is warming the oceans. Warmer oceans are increasing the evaporation. Evaporation or water vapor is one of the very powerful greenhouse gases, is basically producing the conditions inside the atmosphere for the future increase in the temperature. So you see the kind of positive feedback feeding each other. Higher temperature, melting snow and ice, reducing the white areas, changing to darker areas that are absorbing more energy, and by absorbing more, continue to increase the temperature. So these are already observable. You can kind of see them. You can see the consequences of that. There are some very dangerous feedbacks that are slowly starting to appear, and if they get going, we may end up in a very difficult situations because they cannot be easily stopped. One of them is what is happening with the northern parts. I'm going to show you some pictures about Canada, where the higher temperature are melting the permafrost. Permafrost is basically the frozen land, frozen soil, which under the warmer air is being started to melt. And because a lot of organic waste is within that soil, the methane that's been kept within the frozen land is now being released. And methane is about 40 to 50 times more potent greenhouse gas than the carbon dioxide. And if that process starts, there is no kind of way of, stopping it. We cannot refreeze the Arctic or the north of the Canada, Russia, and so on. The other change is also kind of slower change, but already observable. It's a movement of the climate zones. With warming, the conditions are changing. The plant and animal species are migrating and moving. We have, the kind of interesting documents where the grizzly bears and polar bears are living together and sharing the same environment that was never, existing in the past. They're already basically animals that have been caught and analyzed, found that there are already 3 or 4 generations that been going through that change. And you can imagine, how significant that change will be when the kind of whole plants, animals, and everything else, the whole environment goes through that process. So these changes are directly affecting the processes of change, of climate change that we are talking about as a negative impacts on us. Here are some of the responses of infrastructure to change, and these are all real photographs. They're all from Canada except this one. This one is from Alaska. You see, I was telling you about melting permafrost. This is the piece of land that was completely frozen, and now it's in a kind of liquid form with bubbles simply coming to the surface. I never had the opportunity to kind of travel to the north and see that, but some of the colleagues were saying the kids in these northern communities are playing the games and putting this methane on fire. And you can see the whole landscape with the permanent fire is kind of going on from the methane that comes from the regions. This is one of these kind of so-called the northern roads. These roads were obviously taking advantage of the frozen land and used for transport and communication between the south and north. And nowadays there are, very serious issues that some of the communities may not be reachable anymore, except by air. This is what is happening with the buildings that are built on the permafrost. With the melting of the permafrost, you lose the support, and this is what is happening. Another example of the electricity towers, again, because of the foundation, different conditions and melting conditions, the impact is visible. The pipes that are transporting, in our case, mostly oil and gas, are directly being affected by these type of conditions. So you see, almost every type of infrastructure that you can think of is being subjected by the changing conditions, and these are things that we are already kind of trying to deal with. So don't forget, everything is about feedbacks. Everything is about the change that we are introducing that is going to affect us at the end. Now let me give you a few pictures of the future. This first one is a simulation of the change of temperature, global temperature over the next 100 years using one of the modeling tools. I animated the outputs from the Canadian climate model that predicts in this particular graph, you will see the change in temperature. And obviously models are approximations of the reality. They depend and they use the existing knowledge that we have about different processes, and then kind of provide the prediction of the future changing conditions. The message here, I think animation goes to 2100, is very clear. You see how the red and yellow and dark yellow is kind of popping up around the world. Our concern is the region where I live, being very north and relatively close to the, but you can see that even Brazil will be affected to different level. Huge parts of the Asian continent, Africa, and so on. The message is that this warming is continuing, and it's continuing with an even more rapid pace. As a consequence of changing, temperature warming, I already mentioned, the precipitation is changing. Again, picture for Canada. This is Canada, this is United States. And you can see different regions of Canada being the north very much affected, the west being affected. And that's probably of interest to you. The central provinces of Manitoba, Saskatchewan, and Alberta are the prairies, very similar type of conditions as Brazil, and where actually the more dry conditions and droughts will be the consequence of the changing temperature. How is this going to affect particular localities? Not yet very easy to fully determine, but there is a definitely indication from these global models that we are going to experience this kind of shift in the maximum, the mean temperature. The warming is going to kind of create different localities, much more or warmer conditions and much earlier and longer periods of very high temperatures. When you convert the graph like this that shows the kind of mean temperature distribution into number of hot days for different cities across Canada, you see these dark bars are the indications of the major increase in the number of very hot days. Very hot days are considered to be about 30 degrees. And you see even above 35 degrees for different, climate scenarios. So that's one view of the future. In the precipitation domain, you will be observing something like this. This graph is showing the kind of precipitation, basically in intensity, duration, frequency, where the extreme precipitation return periods under the changing conditions will be becoming much shorter, or the precipitation will be much more, extreme precipitation will be happening much more frequently. I did a study for the City of London where we live, and some kind of estimate is that 100-year precipitation event will be, according to various climate models, somewhere in the range between 30 and 25 years. So you can understand how much more frequently very extreme conditions, precipitation conditions, will be hitting the region. That is usually transferred into form of the floods and flooding and very extreme flooding events that are going to affect the population. If you don't look at the change in frequency and you observe the change in the magnitude, you actually realize that for the same return period, the precipitation events will be much higher kind of magnitude. This type of graph is very dependent on the location that you're looking for, but that's generally the message for the region where I am from. Okay, so we know something. We measured the temperature, the precipitation, documented the melting of the ice and the increase in the sea level. We looked a little bit into predictions for the future, which are basically showing the continuation of these kind of processes. So now, how is this related to water resources management, and water resources activities? These kind of changing conditions are definitely requiring us to consider adaptation as a very serious process, to find new and innovative solutions in response to this changing conditions. And the solutions are necessary basically to address the complexity and uncertainty that is growing due to the global change. We have also in the same time very often the kind of integrated impact of the failures of the current management activities, where the climate and the changing global conditions are pushing this whole process to a crisis, and where the mismanagement is, especially mismanagement in the way of looking the water resources problem separate from the people. And I think that is going to contribute even further to pretty serious problems in the future. One of the very characteristic types of mismanagement comes from the our approach to a particular problem where you are trying to address one issue and you push it one place and find a solution and you generate 10 other problems in the other place. This is a very common known kind of system failure, because the reason is because you don't look at the whole system and all the components and the interactions between them. You kind of separate and you focus on particular part of the system. And that's where I think adaptation requires systems approach, requires, I think, the social view of the system, of the water resources, as I was pointing it out, as an integral part of individuals, organizations, and societies being embedded in the environment. When I talk about the kind of systems approach, I mean basically really redefining the problems in the way of identifying the key components, identifying the key feedback relationships, quantifying the values of the variables which are determining the state of the system, and then finding the solution, how to manage and deal with that. That's not trivial. That's pretty hard. And obviously there are some values in the tools and techniques that exist in this area of systems analysis. I was mentioning that lack of standardized approach to bringing the impacts of the changing conditions is one of the major problems. And I'm just kind of going to confirm here the same, where you realize that in the process, we have to start with some kind of projection of the future. We have to bring this information to a local scale, and we need to then process this information to actually come up with different solutions. And these are very high-level steps. Each of these steps can be divided into a much larger number of smaller steps, and the problems are occurring from multiple sources of information, lots of uncertainty. When you are, let's say, trying to determine the future, I already did show you the results of one climate model. The animation was done using the Canadian climate model. There is 39 models around the world. You run each model, you will get a different kind of outcomes. And immediately the question comes, what's the best way? The IPCC or the Intergovernmental Panel is suggesting get them all together and use the median value. Is this the best approach? I'm not sure. I disagree. I feel, depends what you're using the projections for. If I'm trying to kind of find the answers what to do with the particular community where you have a very high density population of the lower income people, I would like to be on a very kind of conservative side of the projection. Or when I'm talking about impact on agriculture and how long the fields will be under the water, I may be less conservative. So it's good to understand the range of uncertainty techniques kind of comes up from the choices of models, from emission scenarios, and other choices that we have. When you have this, one of the main issues is that the scales, temporal and spatial scale of this kind of information is very large. And that doesn't help, making decisions at the local place where you are dealing with a smaller watershed that kind of, requires its own understanding. So we need to downscale that. Downscale temporally, we need to downscale spatially. And, nowadays, if you go through the literature, you will find, there are two categories of downscaling tools, statistical and physical. And then within each of them, you have tons of statistical tools, and you have different dynamic. Dynamic or physical is mostly trying to basically, instead of global climate models, use the regional models with a higher temporal and spatial resolution. But again, these regional models are driven by the boundary conditions established by the global models. So even in downscaling the information to a local level for our use, we have to make choices, and we have various options, and obviously uncertainty that arises from that. And then you go into the process. Let's say you came down with the predicted precipitation. You need to do some analysis for, let's say, flooding and so on. You need first to convert the precipitation into runoff, convert the runoff into kind of flows, run the hydraulic models to assess and get the water depth and inundation, perform some kind of risk analysis based on that, combine the physical information with economic, social, and others. So there is a lot of steps and a lot of issues in that process. So bringing the global change onto the local scale or into our decision-making process. And definitely there is no standardized procedure yet. So the challenges are coming from the fact climate is part of the, and usually what they say, the climate is affecting us through the modification of the hydrologic cycle. Almost every process within the hydrologic cycle, from evaporation, evapotranspiration, infiltration, rainfall runoff, and so on, is affected by changing conditions. So warmer, higher temperatures, and therefore the challenges are going now into almost all the water resources activities, like reduction of the water supply. I think one of the issues that Brazil is dealing very seriously with. Increase in frequency and magnitude of extreme events on both sides, floods and droughts, damage to the shoreline areas from erosion because of the increase in the sea level rise. Insufficient water, that 75% of the global water resources are being used basically for irrigation or for food production. And in the conditions of reduced water supply, food production may become very, serious issues because we will not have enough water to irrigate the fields and produce enough food to support the population of the world. Decrease in the quality of the freshwater sources is another, challenge that is going into, potentials of various technologies in order to deal and treat the water. However, that is immediately affecting the whole kind of economic context because you need to transfer wastewater treatment is expensive. You need to release the funding or take the funding from one sector into this water sector to kind of deal with that problem. And that's where the interactions and the feedbacks are starting to kick in and affect that. Increase in functional and operational requirements for the existing water infrastructure. That's something that we are hardly touching, that most of the existing water infrastructure is designed and planned 50, 60, at least in the developed parts of the world, 50, 60 years ago after the Second World War and so on. And the, the demand for water change, the initial conditions, the climate change, and all the other processes are directly related to what we are still trying to get out of this infrastructure. There are a lot of issues and questions that how the existing infrastructure can first provide the level of service for which it is designed, and then how it can be possibly modified, or how the operations can be modified to respond to new or potentially changing conditions. If you have reservoirs that are being designed and used for hydropower production, water supply, and so on, under the changing conditions of inflow, evaporation, temperature change, and so on, you may need to completely redo the operational strategies for this existing infrastructure. And these are the kind of challenges and the questions I think that you as a young future generation of leaders in water resources management will be dealing with. The questions directly related to water infrastructure are, I think, listed here. We are talking about aging infrastructure. We are talking about insufficiency of funds to manage and maintain that infrastructure. There is no country in the world that's not affected by that. I was talking to your professor today, and we have a figure just for water infrastructure in Canada. We are deficient, or the funds for the maintenance are lacking about $500 billion. So what's the consequence of that? We don't have that money. The infrastructure is not maintained. Not maintaining infrastructure is calling for the failures. Failures can be very dramatic, and then we try and we find the ways how to deal. So we react instead of, kind of preventing that from happening. And this is happening everywhere. This is happening in Western Europe, this is happening in Asia, this is happening in North America, South America, everywhere. Another issue is what I was talking about, complexity, that we have a more complex types of infrastructure and the links between the first additional loads with growing population and changing land use to basically kind of interconnections that are being established between the available water and the location of the available water and the demand and the location of the demand points. In Canada, there is a serious kind of attempt to deal with that, or at least promises being made by the government to deal with that. We have a special federal department, it's called the Public Safety. That department came up with the action plan for the critical infrastructure with the idea of enhancing and preserving the partnerships. Lots being done in trying to link the public and private sources of funding as the solution and the response to this lack of overall maintenance. Implementing the risk management kind of approach, strengthening the critical infrastructure resilience, and that's what I was kind of mentioning at the beginning. The current government promised about $125 billion made the commitment for dealing with roads, bridges, safe drinking water, source water protection, and so on. I do not have figure, and no one is publishing the figure how much of this money has been released and used. Some work is being done, but this is far, far from sufficient. And we are coming to the last part where I would like to talk a little bit about these opportunities. Are we okay with time? Or yeah? So I already kind of mentioned 3 themes and 3 topics are going to kind of, I think, connect all the lectures that I'm going to make during these 5 days. One is, really switch and taking the value of the systems approach into bringing it into practice. Another one is dealing with these uncertainties with kind of risk quantification and transfer from risk to resilience in a quantitative form. And the third one is move from the standards, which are basically based on a statistical information on the statistical analysis of the historical information to something that's basically trying to give you the response of the existing system to changing condition in a really explicit form, and that's what I call the performance-based engineering. Some of this is being done in the area of earthquakes and earthquake engineering, but in water resources we are so far from that. In number of lectures that I was making and talking about that, some of the reaction of the especially professional engineers was, we certainly hope that this is going to stay within academia, that's never going to come into practice. And my answer was, unfortunately, I fully disagree with you, and I think this will be a necessity very soon. So just quickly, the system approach is the totally opposite from the kind of reductionism where you are focusing on a particular problem, you eliminate all the kind of associated issues, and you study that to incredible depth. Some people would say the systems analysis is completely opposite, where we try to actually bring everything into the problem, and then the problem becomes very large, and all the interconnections are relatively hard to follow. But I don't think we have a choice. Any type of reductionist approach is what I think did generate many of the problems that we can see today with the water quality, with insufficient supply, with safety of the infrastructure, failure of the dams and dikes and so on. we need to increase, and today with the support of the computational facilities, powerful computational facilities, I think it's becoming easier and easier to bring and analyze these complex systems in their own way. The second one is that move from risk to resilience. I'll be talking about these things much more in detail, from tomorrow on. But what you see here is one example of the kind of risk-based product. This is the City of London, where I live. The different shades of red are showing basically risk to flooding in the city being caused by changing climate. So for particular return period and particular climate conditions, we analyze the impact on flooding, inundation, and the city paid for this project. We considered 12 types of infrastructure together, calculated the risk, presented in this kind of spatial form, and the product that was very, very well accepted by the city decision makers, because they were now able to see particular locations with a high risk, maybe use that in prioritizing their activities. But at the end, this is still just a single number. At every point, you have one value between 0 and 1, and that is aggregating a lot of messages. What is the reason for that number, that particular risk? What is contributing to it? How that can be changed, affected? We try to build, because the process was such that we did a very detailed analysis for these 12 different types of infrastructure, that when you click on a particular area, you can identify what is contributing to the risk the most. Like in these particular areas, the river kind of goes, here. We identify that the wastewater treatment plants, we have 6 of them in the City of London, all of them located in the floodplain. Very expensive facilities, mechanical equipment, electrical equipment, and everything else, with the changing flooding conditions under the changing climate, that can be inundated and therefore, generate a huge potential damage. And it's interesting, with some small steps, you can change that. It was, I didn't know much later when we finished the study that some of the conservation authorities responsible for the management of the water resources systems in the province of Ontario basically did some changes within. They simply raised the infrastructure to a higher level. Within the same buildings, very small kind of modifications, not extremely costly, potentially reducing the level of damage and level of risk. So useful approach based on this kind of statistical analysis and of the hazards and the impacts, but still limited in a sense of giving us a full understanding how the changing conditions are affecting, in this particular case, the urban environment. And what I am proposing is actually replacement of that single number, which is shown as a color of red in this graph, with, in this map, with this graph. And this graph is now the whole performance of the system over time under the changing conditions. So if you have a city being affected by flood, you can look at the performance of these 12 different types of infrastructure. Let's look at the roads. So the number of kilometers of roads that will be inundated is kind of increasing. That's basically eliminating or decreasing ability for transporting and moving people and so on. It will come to some kind of minimum level of performance, and with the kind of flood passing by, the system will start kind of recovering. So with this temporal and dynamic representation, you now know much more about that particular location, performance of that particular component of the system, and you can adjust your adaptation options to kind of modify that, to maybe bring this black line to a blue line and reduce the potential impact. And I utilize this idea to define and quantify resilience, saying if this is the loss of performance, then the area under the graph can be considered resilience of the system. And by having now these graphs, we were able to calculate, find the value of resilience. And if we introduce the measure to move the black line into a blue line, we can attach that change in resilience as one of the criteria for possibly valuing this option that is moving the graph to a blue condition. I'll talk a little bit more about analytics of that and how that can be done, and I hope you will be considering something that. We did apply that in many places, mostly dealing with flooding in one large project with the hydropower infrastructure. This is the city of Vancouver, and we were looking into health impacts. You see the flood coming into the community. This is the Fraser River, and what we were assessing, utilizing this previous kind of idea of resilience, we were assessing access to health facilities, 2 hospitals located in this location, and then we calculated basically how the people from different locations will be able to access these facilities and how the flood will change that. With inundating these particular roads and bridges and connections, less people will be able to reach the health facilities. And then we kind of connected that space in space. So not only that we got the graph that shows the change of resilience, but we also got the spatial representation for each location, how that graph looks like. So you get like a dynamic map. And that's what I think this, on the upper part, you see the kind of performance curve or resilience curve. And here you see in the different shades, basically the resilience changing. Those who are closest to the hospitals are the least affected. Those who are closer to the river, most affected. And the question will be, so what? What should you do? So this could be a very, very powerful tool to, help you assess, should you increase the dike here? Should you maybe move the people from this particular area to some other location? Should you do something to protect, let's say, the transportation infrastructure and use that as an option? And then you kind of compare the resilience of these 3-4 different options and make potential decision. So that's my idea. And the last opportunity, which I think is essential for you, is this idea of moving from the standards to performance-based engineering, simply because standards are, statistical representation, very similar like risks. They give you a single value. We design a dike for a 100-year return period of flow. What is a 100-year? I did show that, under the climate change, 100-year may be very soon 35 years. So what 100 years should I use? It's becoming very, very, very difficult to do that. The Canadian Standardization Organization is realizing that, and they are looking very seriously in how to replace the standard. And the standards are done, in relationship to temperature, to precipitation, ice, snow, loads, flows, and so on. And what the performance-based engineering is, instead of that single value, is actually using the representation, detailed representation of the system. And this is where I think that the systems approach can be helpful to model the city, to model the piece of infrastructure in details and find out what is the response to particular changing conditions. So we are kind of moving from the statistical analysis of the historical information into something that will require very detailed representation of the physical system, very detailed representation of the disturbance, of the change that affects the system, and then the simulation of the system response to these changing conditions. And this is where you can kind of nicely use the systems model of any problem you have, link that system model to something like resilience graph that gives you the performance of that system under the changing conditions. So these are the 3 opportunities, and this is where I'm coming to the conclusions that you had the opportunity to see. There is definitely impact in increasing risks coming from the climate and global change. The need for adaptation is there, need for standardized approach, and opportunities that may come from the use of systems approach, move from risk to resilience, and performance-based engineering. Thank you very much. There are a couple of papers that are talking about these things. They're all available. You can get them from my website, or you can contact me and get the PDF forms. In this two, I was talking about this kind of risk resilience relationship and performance-based engineering, but we have also lots of papers on the application, like Vancouver case study that I mentioned and other studies. So I'll be talking about more details, over the next 4 days, and you will see. I would like you to consider if you're doing any work and you have interest in flooding next year. I am heading this group of international conferences of flood management, and next year the conference will be organized in US, in Iowa, at University of Iowa, which is celebrating 100 years of hydraulics there. And the call for abstracts is open until November, maybe with your professors. And if you're doing research in this area, please try to join us. We are very much open and would like to see more young people there. And there are special awards for the young people. There are special discounts in the registration. Brazil was heavily involved. The 2 conferences back was the conference in São Paulo. Last one, every 3 years this is organized. Last one was in UK, and this one is coming in US. And the last message is that if you're doing anything related to the systems approach, there is a small leaflet here. I am editing special issue or special issues on the application of the system. So my attempt here is, and the journal was very responsive, is to document various studies from various places in various domains of water resources management that are using this kind of systems approach. It doesn't matter how large, how small the study is, but the point is to try to put together some of the experience that's being gained in different locations over the period of time. So I encourage you as young researchers to consider that the journal is extremely efficient in the process of review and response. I will be obviously responsible of putting everything together, but the process of review will be very much, traditional process the journal is taking. Thank you.
Okay, Professor. Thank you, Professor Simonovic, for your very useful presentation, very open mind. And questions. Preguntas pueden ser en portugués, español, inglés. So we have here undergraduate students, Master of Science, PhD student candidates, and also recent PhD awarded. This is over there. So as a postdocs here.
Congratulations.
This is for last week. Okay, open. So I would like to that you say your name.
Posso falar em português?
Claro, fale tranquila. Acho que a câmera vai pegar. Vai pegar a câmera. Ela vai falar. Tem que levantar, esperar a câmera chegar com você.
Bom, boa tarde a todos. Meu nome é Thaís. Eu sou doutoranda da Universidade Federal de São Carlos, do Departamento de Engenharia Urbana. Eu trabalho com resiliência. O tema da minha pesquisa é a gestão dos recursos hídricos como fator de resiliência urbana. A minha pergunta é o seguinte: eu gostaria de saber se o professor trabalha com indicadores de resiliência hídrica, que é uma das ferramentas que eu pretendo desenvolver na minha pesquisa, porque tudo que ele explicou aqui vem muito de encontro com o meu trabalho, com o que eu venho desenvolvendo. Inclusive, qualifiquei há uma semana atrás, e eu estou criando ferramentas para desenvolver essas tecnologias, enfim, essa infraestrutura dentro da cidade. Então, eu gostaria de saber se realmente eles trabalham com essa questão de indicadores.
Yeah. Yeah, you're going to get that. You're going to get it. I have a very detailed presentation which will explain how you analytically compute this resilience, and also I will illustrate with some results in the application in both domains, in flooding as well as in hydropower infrastructure safety. So you will see more details. This was only, the purpose was to introduce this as an idea that, you know, risk management and risk is useful, risk-based approach is useful, but I think we are moving, and the needs are to understand better the detailed response, and resilience is offering that.
Aos poucos o curso vai ir engrossando mais nas partes quantitativas, né, dos exemplos tirados da prática. Com certeza, nos próximos dias, então vale a pena para você continuar. Hoje foi mais introdutório para mostrar que é importante esse aspecto da resiliência como aspecto social, né, na sociedade.
From the University of Campina, Grande, but they are still typing. I don't have the question yet.
Okay, we are people typing the questions through video conference. Well, some question in terms of you, Professor, as a teacher, what's your opinion about the condition of, that's today in the morning we discussed it also with Felipe, for the next decades, the resilient mechanisms are also dependent on how can we train people to deal with. And of course, higher education, as we are here, but also in primary and secondary schools. So what's your view about that in terms of a whole education process?
But I kind of mentioned, I kind of mentioned already that in my opinion, this is a very significant switch. And the significance is coming from the fact that in order to accept this idea of resilience in this form or any other form, you really need to understand the whole system. And I think this is where the key difference and the transformation is required in education. We need to have much more system-oriented type of training and education, that you understand that the systems are connected, complex, interact, that you understand what is the meaning of the feedback, different feedbacks, how different feedbacks interact. There are some attempts to do that. Our university education is actually very rigid, and especially in engineering in Canada, we have accreditation processes, and having more than one course in the systems is becoming very difficult. But I can tell you that for some private universities in the United States where the government does not regulate or don't care about regulation, Cornell University is approaching the whole civil engineering as an infrastructure system engineering. So the idea is to look at our traditional sciences, to look at different subdisciplines of engineering, but to look at them through this kind of systems approach, definition of the civil engineering systems as infrastructure systems, and then apply the system or put the systems approach through each course in structures, in water resources, in hydrology, in hydraulics, and so on. Another very positive move is an attempt, but very limited, to bring the systems thinking into not undergraduate, into primary education, to actually expose the kids from the early days to systems way of looking at the problems. And there were 3 or 4 schools in the United States. They started with the for kindergarten to 12, K-12. Yeah, K-12 education using the systems approach, where they teach language, for example, using the systems terminology, where they teach, the basic math, using that, physics and everything else. And they were educating teachers at the university to do that, and these teachers were applying This is not spreading very fast because you know that there are lots of regulations related to kind of primary education and so on. But in my opinion, this is something that is probably going to give pretty good and interesting results.
Okay, that's good. Okay, new questions from the internet?
Yes, actually, Professor Simonovic, we have a question from Federal University of Campina Grande, and they said that the opportunities present are very relevant for facing the challenges posed by changes in climate, the environment, and society. The engineer has to take a new role inside this new context. However, including this new approach and perspectives into engineering education to create a new generation of engineers is a great challenge. How do you see this? And they said that you already answered their question.
Partially I answered, but it is a really great challenge, and the challenge is, I think, for us to deal with. And you know, I can, as a kind of senior educator as well as a scholar, advocate that type of education wherever I have opportunity to do that. But you know, in the situations where the governments are regulating the programs, and because engineering is a profession, accredited profession, you need to satisfy the content. It will be a little bit slower process to actually bring that into, I think, into the everyday, into regular education. I think it's important to continue talking about this. In different areas of the world, the approach to education, capacity building, training, is much more dynamic and faster than here. And sorry, not in Brazil, I wanted to say here in Canada. I have a very close contacts with China, and I can tell you that they're going amazingly huge steps in modifying their education. And ideas like what we are now discussing are easily accepted and can be implemented. So even if we, through international collaboration, succeed, you know, in establishing some links, that could be one, you know, way for us to change too. But I think we have to continue talking. This is the reason why I'm working on this issue. This is the reason we are organizing the conference in this issue, why I'm here, you know, to share with you some of these ideas. That's the I think that's the path toward modifying completely and changing the education. Among the practicing engineers, it's not easy to change that. I told you how the person reacted when I was talking about, you know, this idea of modeling the system and CETI, and so, oh my God, the reaction was just don't get that to us. But it will come simply, you know, from these changing conditions which are putting us in a situation, in order to find the answer, we need to approach the problem differently.
Yes. More questions? Mais perguntas? I have some story about that. Sometimes when you need to try to feel like a survivor under a flood, sometimes we need to give lectures in the middle of some 1 meter level of flood, and maintain the cars and the lecture during 1 hour, 2 hours, and with the water level here. And sometimes say, okay, this is a very bad situation. So mostly of us never passed for this situation. And sometimes the difference of having a system approach, you are recognized very, very well, is that you need to pass through a very close experience sometimes. Because it's not theory. It's practice. It's about surviving situation or saving lives.
But the human behavior is something very, very, you know, peculiar, and we are not trained in that. To understand that. I told you the work on that flood of the century changed my view of life. Yeah. Because the people were, you know, you see the people my age and older, which lost everything, you know, from place to live to any savings to any, you know, thing that they had. And imagine putting yourself in a situation like that, like being 50 years old and starting from zero. And it was very interesting. We went through this flooded area of the Red River immediately after the flood, like 2 months after the flood. So everything was very fresh in the memory, the people and the suffering and the evacuations and losses and things like that. So we were talking to a mayor of a very small city that was fully flooded. And he approached me after the presentations and discussions and said, "You are the experts. You tell us what to do. We are going to follow." And we continued, our meetings and so on. We ended up with the reports. When we produced these reports for the governments, we had another round of visiting all the same places where we were. And the same mayor. Okay, so first, one of the key messages of the report was the floods, like flood of 1997, are going to happen again. That they may be even bigger. And the communities and people and everyone needs to be kind of prepared to deal with this kind of floods of the high magnitude and maybe more frequently occurring. So same mayor stand up and say, maybe these recommendations are too strong. Maybe people, because of that, wouldn't like to move to our place, and maybe you should kind of change the language a little bit. And you see in like a period of 2 years, complete change of attitude. Like a human, I think, need and survival instincts are changing the way how we look at it. At the beginning, it was, we needed the help. You are the expert, you tell us. Okay, now we slowly forgetting the bad things, we look at the good things. Well, we would like the further development of the community. Maybe the language should be adjusted to reflect that. So that, how to capture that? How are you going to design the flood protection system that will capture that? To me, that's one of the very, very interesting questions that requires us to understand the human nature, how the human value systems are affecting engineering and the procedures of engineering, math, science, physics. That's all easy to learn and implement, but how to bring this human nature into that and integrate, with the solutions that we may need.
That is the reason some of us are defining ourselves as humanitarian engineers. It's not only to save lives from after a catastrophe, trying to feel as humans first, to understand the other humans suffering for a flood or something like that. So I think we have the first round, the first day was a very nice presentation. Of course, we have time to leave this classroom, and I thank very much Marcelo and also Junior for the very nice facility staff support, and also Felipe and the people from the Campina Grande also attending us. So thank you for coming. Tomorrow at what hour? We are 8:30 here. Please come with your water. Okay, so thank you very much, and we are closing this ceremony. Thank you.